Iapetus, moon, from Wikipedia, the free encyclopedia, at en.wikipedia.org. This recording was last updated on August 22, 2013. Iapetus, sometimes pronounced Iapetus, is the third largest moon of Saturn and 11th largest moon in the solar system. Its radius is about 42% the radius of the Earth's moon, its density about 32.5%, and its mass about 2.5%. Iapetus is best known for its dramatic two-tone coloration, but discoveries by the Cassini mission have revealed several other unusual physical characteristics, such as an equatorial ridge that runs about halfway around the moon. Contents: Section 1. Discovery. Section 2. Name. Section 3. Physical characteristics. Section 4. Temperatures. Section 5. Orbit. Section 6. Exploration. Section 1. Discovery. Iapetus was discovered by Giovanni Domenico Cassini, an Italian-French astronomer, in October 1671. He had discovered the moon on the western side of Saturn and tried viewing it on the eastern side some months later, but was unsuccessful. The pattern continued the following year, as he was able to observe it on the western side but not the eastern side. Cassini finally observed Iapetus on the eastern side in 1705, with the help of an improved telescope, finding it 2 magnitudes dimmer than when on the western side. Cassini correctly surmised that Iapetus has a bright hemisphere and a dark hemisphere, and that it is tidally locked, always keeping the same face towards Saturn. This means that the bright hemisphere is visible from Earth when Iapetus is on the western side of Saturn, and that the dark hemisphere is visible when Iapetus is on the eastern side. The dark hemisphere was later named Cassini Regio in his honor. Section 2. Name. Iapetus is named after the Titan Iapetus from Greek mythology. The name was suggested by John Herschel, son of William Herschel, discoverer of Mimas and Enceladus, in his 1847 publication Results of Astronomical Observations, made at the Cape of Good Hope. In his work, Herschel advocated naming the moons of Saturn after the Titans, all sisters and brothers of the Titan Cronus, whom the Romans equated with their god Saturn. When first discovered, Iapetus was one of the 4 Saturnian moons to be labeled the Sidera Laodicea by their discoverer Giovanni Cassini after King Louis XIV. The other 3 were Tethys, Dione, and Re. However, astronomers fell into the habit of referring to them using Roman numerals, with Iapetus being Saturn V. Once Mimas and Enceladus were discovered in 1789, the numbering scheme was extended, and Iapetus became Saturn VII. And with the discovery of Hyperion in 1848, Iapetus became Saturn VIII, which it is still known by today. Geological features on Iapetus are named after characters and places from the French epic poem The Song of Roland. Examples of names used include the craters of Charlemont and Boligant, and the northern bright region, Roncevaux-Terrat. The one exception is Cassini Regio, the dark region of the moon, named after the region's discoverer, Giovanni Cassini. Section 3. Physical characteristics. The low density of Iapetus indicates it is mostly composed of ice, with only a small amount, around 20%, of rocky materials. Unlike most of the large moons, its overall shape is neither spherical nor ellipsoid, but has a bulging waistline and squashed poles. Also, its unique equatorial ridge is so high that it visibly distorts the moon's shape, even when viewed from a distance. These features often lead it to be characterized as walnut-shaped. Iapetus is heavily cratered, and Cassini images have revealed large impact basins, at least 5 of which are over 350 kilometers wide. The largest, Turgis, has a diameter of 580 kilometers. Its rim is extremely steep, and includes a scarp about 15 kilometers high. Iapetus is known to support long run-out landslides, or stirströms, possibly supported by ice sliding. Section 3.1. Two-tone coloration. In the 17th century, Giovanni Cassini observed that he could see Iapetus only on the west side of Saturn and never on the east. He correctly deduced that Iapetus is locked in synchronous rotation about Saturn, and that one side of Iapetus is darker than the other, conclusions later confirmed by larger telescopes. The difference in coloring between the two Iapetan hemispheres is striking. The leading hemisphere and sides are dark, albedo 0.03 to 0.05, with a slight reddish-brown coloring, while most of the trailing hemisphere and poles are bright, albedo 0.5 to 0.6, almost as bright as Europa. Thus, the apparent magnitude of the trailing hemisphere is around 10.2, whereas that of the leading hemisphere is around 11.9, beyond the capacity of the best telescopes in the 17th century. The pattern of coloration is analogous to a spherical yin-yang symbol, or the two sections of a tennis ball. The dark region is named Cassini Regio, and the bright region is divided into Roncevaux-Terra, north of the equator, and Saragossa-Terra, south of it. The original dark material is believed to have come from outside Iapetus, but now it consists primarily of lag from the sublimation of ice from the warmer areas of Iapetus's surface. It contains organic compounds similar to the substances found in primitive meteorites, or on the surfaces of comets. Earth-based observations have shown it to be carbonaceous, and it probably includes cyano compounds, such as frozen hydrogen cyanide polymers. On September 10, 2007, the Cassini orbiter passed within 1,640 kilometers, that's about 1,000 miles, of Iapetus, and demonstrated that both hemispheres are heavily cratered. The color dichotomy of scattered patches of light and dark material in the transition zone between Cassini Regio and the bright areas exists at very small scales, down to the imaging resolution of 30 meters. There is dark material filling in low-lying regions and light material on the weakly illuminated pole-facing slopes of craters, but no shades of gray. The dark material is a very thin layer, only a few tens of centimeters, approximately 1 foot, thick, at least in some areas, according to Cassini radar imaging and the fact that very small meteor impacts have punched through to the ice underneath. NASA scientists now believe that the dark material is lag, or residue, from the sublimation, or evaporation, of water ice on the surface of Iapetus, possibly darkened further upon exposure to sunlight. Because of its slow rotation of 79 days, equal to its revolution and the longest in the Saturnian system, Iapetus would have had the warmest daytime surface temperature and coldest nighttime temperature in the Saturnian system even before the development of the color contrast. Near the equator, heat absorption by the dark material results in daytime temperatures of 129 Kelvin in the dark Cassini Regio compared to 113 Kelvin in the bright regions. The difference in temperature means that ice preferentially sublimates from Cassini and precipitates in the bright areas, and especially at the even colder poles. Over geological timescales, this would further darken Cassini Regio and brighten the rest of Iapetus, creating a positive feedback thermal runaway process of even greater contrast in albedo, ending with all exposed ice being lost from Cassini. It is estimated that over a period of 1 billion years at current temperatures, dark areas of Iapetus will lose about 20 meters of ice to sublimation, while the bright regions would lose only 10 centimeters, not considering the ice transferred from the dark regions. This model explains the distribution of light and dark areas, the absence of shades of gray, and the thinness of the dark material covering Cassini. The redistribution of ice is facilitated by Iapetus's weak gravity, which means that, at ambient temperatures, a water molecule can migrate from one hemisphere to the other in just a few hops. However, a separate process of color segregation would be required to get the thermal feedback started. The initial dark material is thought to have been debris blasted by meteors off small outer moons in retrograde orbits and swept up by the leading hemisphere of Iapetus. The core of this model is some 30 years old and was revived by the September 2007 flyby. Light debris outside of Iapetus's orbit either knocked free from the surface of a moon by micrometeoroid impacts or created in a collision, would spiral in as its orbit decays. It would have been darkened by exposure to sunlight. A portion of any such material that crossed Iapetus's orbit would have been swept up by its leading hemisphere, coating it. Once this process created a modest contrast in albedo, and so a contrast in temperature, the thermal feedback described above would have come into play and exaggerated the contrast. In support of the hypothesis, simple numerical models of the exogenic deposition and thermal water redistribution processes can closely predict the two-toned appearance of Iapetus. A subtle color dichotomy between Iapetus's leading and trailing hemispheres, with the former being the more reddish, can in fact be observed in comparisons between both bright and dark areas of the two hemispheres. In contrast to the elliptical shape of Cassini Regio, the color contrast closely follows the hemisphere boundaries. The gradation between the differently colored regions is gradual, on a scale of hundreds of kilometers. The next moon inward from Iapetus, chaotically rotating Hyperion, also has an unusual reddish color. The largest reservoir of such infalling material is Phoebe, the largest of the outer moons. Although Phoebe's composition is closer to that of the bright hemisphere of Iapetus than the dark one, dust from Phoebe would only need to establish a contrast in albedo, and presumably would have been largely obscured by later sublimation. The discovery of a tenuous disk of material in the plane of and just inside Phoebe's orbit was announced on 6 October 2009, supporting the model. The disk extends from 128 to 207 times the radius of Saturn, while Phoebe orbits at an average distance of 215 Saturn radii. It was detected with the Spitzer Space Telescope. Section 3.2 Overall Shape. Current triaxial measurements of Iapetus give it dimensions of 746 by 746 by 712 kilometers, with a mean radius of 734.5 plus or minus 2.8 kilometers. However, these measurements may be inaccurate on the kilometer scale, as Iapetus's entire surface has not yet been imaged in high enough resolution. The observed oblateness corresponds to a rotation period of 10 hours, not to the 79 days observed. A possible explanation for this is that the shape of the moon was frozen by formation of a thick crust shortly after its formation, while its rotation continued to slow afterwards due to tidal dissipation, until it became tidally locked. Section 3.3 Equatorial Ridge. A further mystery of Iapetus is the equatorial ridge that runs along the center of Cassini Regio, about 1,300 kilometers long, 20 kilometers wide, and 13 kilometers high. It was discovered when the Cassini spacecraft imaged Iapetus on December 31, 2004. Peaks in the ridge rise more than 20 kilometers above the surrounding plains, making them some of the tallest mountains in the solar system. The ridge forms a complex system, including isolated peaks, segments of more than 200 kilometers, and sections with 3 near-parallel ridges. With the bright regions, there is no ridge, but there are a series of isolated 10-kilometer peaks along the equator. The ridge system is heavily cratered, indicating that it is ancient. The prominent equatorial bulge gives the moon a walnut-like appearance. It is not clear how the ridge formed. One difficulty is to explain why it follows the equator almost perfectly. There are at least 4 current hypotheses, but none of them explains why the ridge is confined to Cassini Regio. Hypothesis number 1. A team of scientists associated with the Cassini mission have argued that the ridge could be a remnant of the oblate shape of the young Iapetus, when it was rotating more rapidly than it does today. The height of the ridge suggests a maximal rotational period of 17 hours. If Iapetus cooled fast enough to preserve the ridge, but remained plastic long enough for the tides raised by Saturn to have slowed the rotation to its current tidally locked 79 days, Iapetus must have been heated by the radioactive decay of aluminum-26. This isotope appears to have been abundant in the solar nebula from which Saturn formed, but has since all decayed. The quantities of aluminum-26 needed to heat Iapetus to the required temperature give a tentative date to its formation relative to the rest of the solar system. Iapetus must have come together earlier than expected, only 2 million years after the asteroid started to form. Hypothesis number 2. The ridge could be icy material that welled up from beneath the surface and then solidified. If it had formed away from the position of the equator at the time, this hypothesis requires that the rotational axis would have been driven to its current position by the ridge. Hypothesis number 3. Iapetus could have had a ring system during its formation due to its large hill sphere, and that the equatorial ridge was then produced by collisional accretion of this ring. However, the ridge appears too solid to be the result of a collapsed ring. Also, recent images show tectonic faults running through the ridge, apparently inconsistent with the collapsed ring hypothesis. Hypothesis number 4. The ridge and the bulge are the result of ancient convective overturn. This hypothesis states that the bulge is not composed of non-hydrostatic structures, but is built of less dense matter and is in isostatic equilibrium. The ridge is also built of less dense matter. Its position among the equator is probably a result of the Coriolis force acting on a liquid interior of Iapetus. Section 4. Temperatures. Temperatures on the dark region's surface reach 130 Kelvin, that's negative 143 degrees Celsius or negative 226 degrees Fahrenheit, at the equator, as heating is made more effective by Iapetus's slow rotation. The brighter surfaces absorb less sunlight, so temperatures there only reach about 100 degrees Kelvin, that's minus 173 degrees Celsius or minus 280 degrees Fahrenheit. Section 5. Orbit. The orbit of Iapetus is somewhat unusual. Although it is Saturn's third largest moon, it orbits much farther from Saturn than the next closest major moon, Titan. It has also the most inclined orbital plane of the regular satellites. Only the irregular outer satellites like Phoebe have more inclined orbits. The cause of this is unknown. Because of this distant inclined orbit, Iapetus is the only large moon from which the rings of Saturn would be clearly visible. From the other inner moons, the rings would be edge-on and difficult to see. From Iapetus, Saturn would be 4 times the size of the moon viewed from the Earth. Section 6. Exploration. Iapetus has been imaged multiple times from moderate distances by the Cassini orbiter. However, its great distance from Saturn makes close observation difficult. There has been one close targeted flyby at a minimum range of 1,227 kilometers on September 10, 2007. No additional close flybys are planned. One viewing opportunity is possible in 2015. You have just finished listening to Iapetus, Moon, from Wikipedia, the free encyclopedia. This recording was last updated on August 22, 2013. This sound file and all text in the article are licensed under the Creative Commons Attribution Share Alike 3.0 Unported license, available at creativecommons.org/licenses/by-sa/3.0.